Welcome back to real time digital signal processing course. So, today we will discuss about overlap add method, how to use our F15 for the continuous time signal. So, coming to the recap of it, so we have completed FFT, its butterfly structure, and then we have seen some examples using both DFT and then FFT. So, how to use FFT in for overlap add method. So, we will see some of the definitions. So, we will see modulo indices and how it is going to be used for the periodic repetition. So, as we can see here, anything n with capital N is our length of FFT. So, it is equivalent to n itself. What does it mean? That is, mod of n is nothing but remainder of n by n. So, in this case x of n, if we have 4 samples, so we say that it is periodic with period 4. The repeated pattern will consist of what is it, x of 0, x of 1, x of 2 and then x of 3, and the length is n. Then we say that the repetition is going to happen after x of n minus 1 samples. N is usually we take it power of 2. So, as we have seen in the example, n is equal to 4 what we have taken. So, we have seen the repetition what it is going to happen. So, we will see visually here n is going to vary from minus 4 to 8 is the long sample what we have taken, and then small n which is going to repeat after 4, that is 0, 1, 2, 3, and then later on again 0, 1, 2, 3 and 0, 1, 2, 3 and then the last one is 0. So, we say that n by n is nothing but integer plus a non-negative integer which is less than n divided by n. As an example, so because we have taken capital N is equal to 4, so the fifth sample what we have to take it, then what is the thing is going to happen? This is 5 by 4 which is nothing but 1 plus 1 by 4. So, this is what the integer plus non-negative integer what we are taking it. Here if it is minus 2 by 4, then the integer is going to be minus 1 plus 2 by 4. This should be non-negative integer what we have to assume. So, this is how we will be taking the modulo indices, and then after that it is going to repeat. So, what we are going to do with overlap during the periodic repetition. So, we say that periodic repetition makes an aperiodic signal, that is x of n. So, periodic to produce x tilde of n. So, there are two important parameters in this case, that is the smallest support length of the signal x of n what we needed, and period n used for repetition that determines the period of r x tilde of n. So, we call I smallest support length which is greater than period of repetition, and repeating the thing I, there will be overlap. I will be the smallest support length period of repetition, and I, there will be no overlap. These are the condition, there will be overlap and no overlap condition, and x of n can be recovered from our periodic signal x tilde of n. So, how do we represent our x tilde of n is equal to I is equal to minus infinity to infinity x of n minus I n. So, I will be defined with these parameters. So, to show that how the periodic repetition is going to be, that is if we consider no overlap and then n is taken as 4. This is our x of n, then what happens to our the repeated signal at L is equal to 0. So, we know that we have 4 samples here, then this is our x of n, then at L is equal to 1 it is going to be x of n minus n, that is we are repeating the 4 samples. Same thing at L is equal to 2 we will be repeating x of n minus 2n. So, that is what dot dot what we have it. And then what happens on the negative side of it? It is going to be L is equal to minus 1, it is going to be x of n plus n actually. So, the 4 samples are repeated here same way, and then all of them get added, and then we will be seeing that there is no overlap. The support length what we have taken is 4 is which is equal to n. So, our x tilde of n, you will be seeing that this is the x of n, and then this is L is equal to 1, and this side L is equal to minus 1. So, you will be seeing the repetition of it. This is the periodic repetition what is shown pictorially. So, coming to if there is a overlap, that is periodic repetition, how it is going to look, what we will see it here. So, here also taken as n is equal to 4. So, what we have is our x of n sample has 6 samples in this case, and then we are taking n is equal to 4. So, initially what we have is 6 samples at the 0 basically, then x of n is put in. Since it is repetition, what we have is n is equal to 4, you will be seeing that there is a overlap on the positive side as well as on the negative side. So, you are seeing that there are 2 of them have been repeated on this. So, you will be seeing that they are overlapping, even here it is going to overlap. Then what happens to our x tilde of n? So, we say that support length is 6 which is greater than n, then we will be seeing that because we are adding them up. So, you will be seeing in the magnitude which has got increased with these 2 samples, the other 2 samples remain same. So, you will be seeing that this repetition is going to happen on the positive side as well as on the negative side. So, one has to keep it in mind that how the periodic repetition is going to have a overlap when our length is greater than our n. So, coming to the thing, we will see that how we are going to have the periodic repetition. Once again what you will be seeing the thing. So, you have x of n here. So, then what is the thing is going to happen, only we are taking the samples here which are length 4. So, you will be seeing that the magnitude of them is 2101, and then x of n has support for n is equal to 0 to n minus 1. Then our x of n capital N will be, it is n mod n, what we will be taking it as x tilde n, which is given by the equation I is equal to minus infinity to infinity x of n minus I n. So, how this is going to be represented? So, this is our x of n, this is what we have taken the thing. So, when we do the repetition, you will be seeing that modulo of n is going to be 2, 1, 0, 1. So, because the support size and period size are the same, there is no overlap when taking the periodic repetition of our x of n. So, you will be seeing that it is same. So, now coming to the this thing modulo indices, same thing, periodic repetition, how it is going to look like, what we will be seeing with the thing. So, you will be seeing that the same values have been taken 2, 1, 0 and 1, and then when we take the modulo of it, so you will be seeing that it is going to go in the 0th here, then minus 1 will be, this is the way, and then 1, next what we are going to have the thing. So, it will be repeating the value at different intervals what it is shown here. So, which is shown again in this manner. So, from here to here what we will be going, from here to here, and from there we can show it pictorially that this is the way what we are going to represent in the periodic form. So, that is x of n modulo n is nothing but our repetition x tilde of n, which is shown there. So, from here what you can draw your diagram as x and y coordinates, repetition of x of n in this manner. So, now we have to look in for the circular convolution. So, you must be remembering we have taken some examples and then we repeated the computation of the circular convolution. So, there are two interpretations. The first interpretation what we will see it. So, we are assuming x 1 and x 2 have support n is equal to 0 to n minus 1. Then take the periodic repetition of our x 2 of n with period n. We are assuming both are of the size n in this case. Then what happens? It is going to be k is equal to 0 to n minus 1, x 1 of k into x 2 of n minus k modulo n what we are going to take it, or we can write it x 2 of k into this thing modulus of r x of x 1 basically here. So, both are the same thing. So, we can use any one of them. So, conduct a standard linear convolution of x 1 and then x 1 and x 2 tilde n for n is equal to 0 to n minus 1. So, we remember that circular convolution has the symbol like this, x 1 n convolved with x 2 of n, or the other way round what we will be seeing it, x 1 of n convolved with our this thing linear convolution x 2 periodic tilde of n what we can give it, which is same. So, this is the equation. So, what we have it. So, we will be seeing that this is minus infinity to infinity. So, we cannot compute in our hardware. So, it will be reduced from 0 to n minus 1 x 1 of k into x 2 tilde of n minus k. So, what happens to the circular convolution of it? It is going to be 0 for n less than 0, that is what we have assumed, and n greater than or equal to n, this is what we have given the equation. So, that is it makes sense, that is what we take it, since x of n modulo of n is nothing but our repetition x tilde of n. So, another interpretation is what is it? So, they have the support of 0 to n minus 1. So, we are going to take the periodic repetition of x 2 of n with period n in this case. So, you will be seeing that x 2 of n minus k n, and then we conduct the linear convolution instead of circular convolution. We will be doing the linear convolution of x 1 and x 2 for n. Then what happens? x l is represented as the linear convolution of n is given by x 1 of n linearly convolved with x 2 of n. So, equation what you are seeing minus infinity to infinity. So, which is going to be reduced to k is equal to 0 to n minus 1 for the implementation, x 1 of k into x 2 of n minus k. So, compute the periodic repetition of your x l of n and window the results for n is equal to 0 to n minus 1. So, you will be doing x 1's circular convolution is equivalent to x 2 of n, which is nothing but our a is equal to minus infinity to infinity x l of n minus I n for n is equal to 0 to n minus 1. So, what are the two methods? First, we can do the circular convolution by taking the modulo of one of the signal, or we can do the linear convolution of the signal and do the circular convolution at the output, that is what it is shown. So, we know that filtering of long data sequence, how we are going to use our FFT. So, as we have already discussed, we have n is equal to 8 and 8 point FFT is given by this butterfly structure. So, you have seen the thing. So, if it is 16 you can extend it and 32 and so on. So, it is easy to write n is equal to 8. So, which we can use it. So, how we are going to take care of the long data sequence that we want to filter it? We say all n input samples are required simultaneously by the FFT operation. So, complexity of n and FFT is what we have taken n log 2 n basically, and if we use the symmetry property it will be n by 2 log 2 n. So, if n is too large as for long data sequences, then there is a significant delay in processing that precludes our real time processing. That is, we are going to have a time constraint on the thing, because we do not know the length of the signal which is going to come continuously in real time. So, how we are going to take care of this? We cannot have as long as we want. So, then what we do is we give the input signal here, we get it from the data acquisition delay what we are going to consider, and then we will be adding our data processing delay also. This is acquisition as well as processing, then we will be giving the signal out. This is our real time processing what it is going to happen. So, we will see the thing. So, for the first case today what we will consider is the overlap add method. So, in the next class we will consider the overlap save method. So, what is that overlap add method? This is going to deal with some of the signal processing principle what it is written here. So, what is it? We are going to have the linear convolution of a discrete time signal of length L, what we are going to restrict, and a discrete time signal of length M, where what we are going to get the output is L plus M minus 1. So, that is we are using the additivity property here, x1 of n plus x2 of n convolved with our h of n is going to give us x1 of n convolved with h of n plus x2 of n in, convolved with h of n. So, that is what we are looking at it. So, now we will see the thing. So, what we have is input x of n is divided into non overlapping blocks basically, and xm of n each of length L what we will be considering in this, and then each input blocks xm of n is individually filtered as it is received to produce the output block ym of n. So, you will be seeing as a picture really here. So, you are considering L is equal to 1 first, that is the length in this case is n is equal to 4 what it has been taken. So, this is the first length which is going to be convolved with h of n. So, the other length what we will be considering is L is equal to 4, L is equal to 2, 3 and then 4. So, in this whatever x of n signal, so we have 4 L basically. Now, what we have done the thing, so we have separated according to the length. So, I have 4 values in this, we will do the convolution of it, and the next one is convolved with h of n is convolved with x2 of n. Then later on as you can see it, we are adding with the previous one. So, the next one is getting added with the x3 of n. So, you will be seeing that these are the 4 samples which is in x3 of n which is getting convolved, and then you will be going on till you finish your input, or if it is continuously coming, this is the process which is going to be repeated forever. So, what is the filtering stage? So, we make use of that is NDFT and NIDFT, where n is the length of our this thing DFT or FFT length, which is going to be L plus M minus 1. And then we are going to do the 0 padding of x of n and h of n. So, that are of length L what we call it, m is less than n is required in this case. So, the actual implementation of the DFT IDFT will use the, as we know that for fast Fourier transform what we will be using it, and then inverse fast Fourier transfer for computational simplicity. So, how we are going to use the DFT for linear convolution? So, first we are going to take xm of n which has the length 0 to L minus 1, and h of n is the other length which has the support n is equal to 0 to m minus 1. So, we set, that is in this case one of them is the signal h of n. If it is the filter case, we will be seeing that if it is a FIR filter, we will be having the B coefficients, the basically, or h of n can represent the coefficients of the filter. So, this is one length, the other one is L length, input length. Then we set n is greater than or equal to L plus m minus 1, that is the length of linear convolution result, and 0 pad are x m n and then h n to have support for n is equal to 0 to n minus 1. So, in the lab class we have seen that how we can do the 0 padding, even two problems what we have taken, how by 0 padding we can make it same length and then do the FFT on the two signals. So, then what we are going to do it? So, we are going to take first NDFT of x of m to give x m of k. K is varying between 0 to n minus 1 in this case, and then the next one is take NDFT of h of n to give us h of k, which is k also will be between 0 and minus 1. Then we know that in the frequency domain, when we have two DFTs, it is only the multiplication between the two signals, that is ym of k is nothing but xm of k into h of k for k is to 0 to n minus 1. So, once we have done the multiplication, we know that the result is available, then we can take the IDFT, NIDFT of ym of k to give our ym of n. So, you must be wondering why we have to do all these things, why not sigma. So, in the last class we have seen that with 512 points DFT computation cost and then FFT computation cost, and what the frequency will be achieving, although we are doing this 4 times basically or 3 times we call it, because NDFT 2 of it and NIDFT cost is same basically, and in between we have to do the complex multiplication. In spite of the thing, our computation time or the frequency of operation is higher than the normal DFT, and even which is equivalent to our linear convolution. So, now we will see how we are going to do this linear convolution via the DFT. So, length of linear convolution result is equal to length of DFT, what we are going to get it. So, this is our 4 samples. So, we are repeating the things, same 4 samples on both the sides, left and then right hand side, and we have assumed there is no overlap, and then we have assumed support length is 4, which is n is equal to 4, and we can see that here x of n what we have is the 4 length, and then the repetition on the r x tilde of n. So, now we will see how we are going to overlap add addition stage. So, from the additivity property, since our x of n is equal to x1 of n plus x2 of n plus x3 of n, you can go on. So, which is nothing but m is equal to 1 to infinity xm of n. So, this is what we have the convolution. So, we will be using x of n convolved with h of n, which is nothing but x1 of n plus etc. total going to be convolved with h of n, or because of the our additivity property. So, we can do them individually. So, that is xm of n convolved with h of n, m is varying between 1 to infinity, and then what we call it as summation of all of them individually done xm of n. So, we will be adding all y's basically, that is n is equal to 1 to infinity, ym of n will be giving us the complete overlap add output. So, as we can see the thing here, so this is the length what we have it, we are going to convolve with h of n and we will be generating the linear convolution. So, we know that it is going to give us L plus m minus 1 length here. So, that whatever this extra m minus 1 samples, that is we call it as uh, which is going to be in connection, we will be discarding them, okay, or we can take it to the next one and then use, that is add to the next block basically. So, this is first y1 of n, and then these two are going to be added to the next block, and then we will be making it as L is equal to 4 length here, as you can see the thing. So, 2 samples will be coming from there, these two are from m minus 1, which is 2 will be from this block, what will be coming, and then we will be using that to compute our here also y2 of n, and then later on it is y3 of n. So, you will be adding these two samples, as you can see that they are getting repeated in successive, that is the m minus 1 samples are repeated in the next blocks for our computation. So, we call y of n is nothing but x of n convolved with our h of n. So, the support overlap amongst ym blocks must be accounted for, that is what the one has to keep it in mind. So, how the thing is going to happen, we have this figure shows in I think that was little small. So, you will be understanding the thing. This is my complete input. So, we have bifurcated into L chunks of them, as you can see it. We call them as x1 and x2 of n. So, you are seeing from this m minus 1 what we will be adding as zeros in this case, and here also we will be adding m minus 1 zeros. So, you will be seeing that you are adding m minus 1 zeros with x1 of n, x2 of n, and then x3 of n. Then what will be our output? This is y1 of n, and add this m minus 1 zeros to this one, that is you will be appending on the y2 of n, and then we have on the other side also m minus 1 zeros. So, this one is going to be added m minus 1 zeros with y3 of n, and so on, what we will be having the output. So, we have overlap add method, how it is going to work, what is shown in here algorithm, what it has to be written. So, what is it? First, break the input signal x of n into non overlapping blocks of x m of n of length L, and then we are going to do the 0 pad h of n to be of length n is equal to L plus m minus 1, and then we take n DFT of h of n to give our h of n basically k is equal to 0 to n minus 1, h of k here for k is equal to 0 to n minus 1. So, for each block m we are going to 0 pad x m n to be of length n is equal to same thing L plus m minus 1, and then we are going to take n DFT of x m of n to give x m of k here for k is equal to 0 to n minus 1. So, multiply y m k with x m of k, what we have got it here, with that of h of k. This should be h here, h m of n to give our h m of k. Then these are the two signals what we have taken the DFT, and then we will be multiplying it, and then take n IDFT of y m of k, what we have got it, to give y m of n. For n will be, because inverse DFT, n will be varying between 0 to n minus 1. So, then the fifth step is form y of n by overlapping the last m minus 1 samples of y of m of n with the first m minus 1 samples of y m plus 1 n and adding the result. So, this is how we will be doing it. We will take up an example and then show that how we have done the overlap add method. Thank you. And in the next class we will cover overlap save method. So, both of them should give us the same results. Thank you.